Dear colleagues, my name is Alexander Belov. I'm an associate professor in Samara National Research University. Let me introduce the work that was made by me and my co-author Anna Denisova. The topic of this work is super resolution reconstruction of remote sensing image using multi-temporal images with partial scan distortions. Sometimes we face it with situation when we have a number of satellite images with different spatial and spectral characteristics for the same territory, and some of them are cloudy, for example, and the sphere idea is not to exclude cloudy images from the further processing and use all available data to get some more extra information. The goal of the work is to develop a remote sensing data fusion algorithm in order to increase spectral and spatial resolution under conditions when scan distortions are present. The scan distortions are considered significant local brightness changes in the scan caused by overlapping part of the scan with an opaque object or its shadows at the moment of image acquisition. Such distortions are an essential problem for the multi-temporal image fusion algorithms. In particular, the existing approaches require meeting two conditions. On the one hand, there should be a sufficient number of images, and on another hand, the fused image should be cloudless. It is without any scan distortions. These two requirements are conflicting because often an increase in dataset size is possible only due to partially cloudy images. So it becomes interesting to consider the implementation of an image fusion algorithm using partial distortion data. Let me start with our data acquisition model. It's described by the following expression. We will assume that the scan X is captured by K imaging systems at different time moments tk. The observed low resolution image is formed as a result of spectral sampling, effect of a sensor optical system, random frame shift due to errors of georeferencing, and a spatial discretization operator. The observed high-resolution image can be represented as a sum of unchangeable part of the scan and part of the scan with changes. Here S is the mask of scan distortions. Let's consider the average image for each imaging system, converted to spatial coordinates of high-resolution image. It is clear that the second term defines intensity distortions which are caused by scan distortions. To exclude such distortions from further processing, let us consider a modified observation model with a modified distortion mask sigma, containing only non-zero samples of the distortion mask affected by spatial distortion operator A. The fusion task is formulated as a minimization of the average image representation error for each imaging system, assuming BTV regularization is used. The second component of the optimization functional is regularizing term. The essence of proposed method is the solution of the optimization problem using a gradient descent approach. Here you can see the scheme of the proposed algorithm. It includes the following steps. calculation of the average image for each imaging system, calculation of initial approximation, and then calculation of the reference image estimation using iterative procedure based on gradient descent approach. Experimental study was carried out for modeling image with sand distortions. Cumulus clouds and their shadows were considered as distortions. Firstly, the clouds and their shadows were embedded into the hyperspectral Averus image, and then observed low-resolution images were simulated. Here you can see examples, images with distortions and without. Data modeling was performed for two imaging systems with the following parameters. Here you can see the spectral characteristics for imaging systems. Here you can see spectral characteristics of reference image and some experiment parameters. In the experiment, a mixed dataset contained an equal number of images with and without sand distortions were considered. Each image with sand distortion contained 10% of distorted pixels. This graph shows that the image reconstruction error using the full dataset is less than the image reconstruction error using only image only images without any sand distortion. Average correction value of mean square error of image fusion presented in the table. This table shows the result of experiment carried for data with different signal-to-noise ratios. In all cases, the reconstruction error using the full dataset is less than using distortion-free images only. So we can conclude that using additional data is a good idea, especially in the case of small datasets. This slide shows examples of source data and the data examples of source data with and without distortions for system 1 and for system 2. And here you can see results of processing fusion result for the mixed dataset, and fusion result for pure dataset. It is only images without any sand distortions. So you can see that recovery results for the mixed or full dataset is more contrast and more detailed than this one. So now we can conclude that the proposed algorithm provides super resolution image fusion with a data set containing images with sand distortions. For mixed data sets containing both images with and without sand distortions, using of whole dataset allows to decrease fusion error in comparison with the result obtained only with the use of distortion-free images. And if the dataset contains only images with sand distortions, the proposed algorithm provides super resolution fusion because it eliminates distorted parts from the further fusion process. Thank you for your attention.